Usually, like, when we picture exercise recovery, we kind of envision the catastrophic.
Oh, absolutely. The worst case scenario.
Right. We imagine the human body like an automobile engine, just pushed to its absolute limits. You redline that engine in first gear until it smokes, a gasket blows, and the mechanic just points at the melted metal.
Yeah, the problem is obvious.
Exactly. And extreme muscle soreness, it operates on that same highly visible level.
It does. And the scientific literature has historically mirrored that exact bias. I mean, we've heavily studied what happens when tissue is pushed beyond its failure point.
Because it's easy to see.
Yeah, because the resulting inflammation and structural damage are just undeniable. They're super easy to measure.
But like daily athletic training paints a completely different landscape for you and me. When you look at the routines of people who actively exercise week in and week out, we aren't looking at blown engines.
Not at all.
We're looking at the murky, subtle physiological changes that happen when you put in the miles, but purposefully stop short of total destruction. So, welcome to the deep dive.
Glad to be here.
Our mission today is to explore the physiological mechanisms of recovery for you, the listener. We really want to understand how your back muscles and connective tissues respond to the kind of regular submaximal workouts you actually do.
Right. It's the stuff you do on a random Tuesday.
Exactly. And crucially, we're going to determine whether manual therapy truly accelerates that recovery at a cellular level, or if it, merely provides psychological comfort.
And what's fascinating here is that by shifting our focus to submaximal exercise, we strip away all the chaotic, screaming noise of extreme inflammation.
So we get a clearer picture.
Precisely. We finally get to observe the nuanced mechanical responses in both the muscle and the often ignored fascial layers, and we do it without the distortion of a massive physiological crisis.
To accomplish this, we are pulling from a meticulously designed piece of literature. This was published in the Journal of Sports Science and Medicine in 2024.
It's a great paper.
It really is. The article is titled, Effects of a Manual Treatment on Lumbar Microcirculation and Tissue Stiffness, following Submaximal Eccentric Trunk Extensor Exercise, a randomized controlled trial.
Quite a mouthful, but very descriptive.
Definitely. And it was authored by a robust team of researchers. We've got Andreas Brandl, Michael Keiner, Jan Wilke, Christoph Egner, Robert Schleip, and Tobias Schmidt.
And the methodology they deployed, it fills a glaring gap in our understanding. I mean, most studies induce severe delayed onset muscle soreness DOMS by forcing unaccustomed maximal exertion.
Right, making people do things they never do until they completely fail.
Exactly. But athletes adapt. They train with fuel left in the tank. So this research team engineered a laboratory scenario to mimic that exact reality.
So how did they set this up? Well, they brought in 21 healthy participants, and they specifically selected individuals who already engaged in more than 4 hours of physical activity a week.
So these aren't beginners.
Right. These were trained bodies, already adapted to mechanical stress. The researchers put them on a back extension bench and had them perform an eccentric exercise protocol.
Which is key here.
Yeah, for those visualizing this, the participant leans forward over the bench, flexing the trunk down to a 40-degree angle, and then returns to a neutral position. The eccentric phase is that slow lowering motion, where the muscle lengthens while under tension.
And eccentric movements are, highly effective at triggering microscopic structural changes.
Because of the pulling.
Exactly. When a muscle fiber attempts to contract while an external force simultaneously pulls it apart, the physical strain damages the microscopic proteins within the muscle cells, things like actin and myosin.
Wow.
Yeah, and this mechanical tension is the primary driver of both athletic adaptation and that delayed soreness we all know.
But the researchers instituted a strict limit on that strain, right? They instructed the participants to stop the exercise when they reached a rating of perceived exertion of 7 or 8 out of 10.
They didn't let them go to failure.
Right, they averaged about 41 repetitions. And when compared to the extreme DOM studies, that volume is only about 70% of their maximum capacity.
It's the equivalent of driving on the highway at 70 miles per hour instead of redlining the engine.
Exactly.
Yeah.
But if they aren't going to failure, are we even going to see measurable damage? Is a 7 out of 10 enough to leave a structural footprint we can actually analyze?
Oh, a submaximal load absolutely creates micro tears at the cellular level.
Okay.
The vital question the study asks is where those micro injuries are localized. The researchers really wanted to differentiate between the physiological response of the erector spina, the thick, primary muscles running parallel to your spine.
The big back muscles.
Yeah, they wanted to see the difference between those and the thoracolumbar fascia.
Ah, the thoracolumbar fascia, or TLF. That acts as a massive transmission belt for the back. It's this dense, rhomboid-shaped network of connective tissue that wraps around the muscles.
And it is heavily innervated with free nerve endings. It plays a massive role in spine stability.
Which is why, when people complain of vague lower back pain, often the TLF has become fibrotic and lost its ability to stretch and glide.
Exactly. So knowing the TLF's role in back pain, the researchers needed to observe how it responded to that highway mileage workout. And more importantly, how it responded to a manual intervention.
Okay, let's unpack this intervention phase. So the participants finished their 41 repetitions. Their backs were fatigued, but like we said, not destroyed.
Right.
The researchers immediately split them into two groups. Group 1 received the actual treatment, which is myofascial release, or MFR, administered by an experienced osteopath.
And this was very standardized.
Yeah, it consisted of 8 to 10 minutes of 5 highly specific techniques. They applied sustained manual pressure on the lateral raphe, which is the junction where the abdominal muscles connect to the back fascia. They utilized lateral stretching, and they performed longitudinal sliding directly up the paravertebral muscles using an open fist, applying a moderate targeted force of 25 to 100 newtons.
And that specific range of force, applied at a slow velocity, is the defining characteristic of myofascial release.
It's not just a standard massage.
Right, it's not. The objective is to physically engage the tissue layers and restore their shearing capacity.
Shearing capacity.
Yeah, which is basically their ability to glide smoothly over one another without catching or adhering.
Makes sense. But to measure whether that mechanical pressure actually worked, the researchers needed a control group. And this is where it gets wild.
Oh, I love this part.
Group 2 received a sham laser therapy, literally a fake green light. Both the therapist and the participant wore protective goggles to sell the illusion of a high-tech medical procedure.
It's brilliant.
And a post-treatment questionnaire confirmed the placebo was flawless. Both groups genuinely believed they received a legitimate medical intervention.
They bought it completely.
But I understand the need to isolate variables, but I have to push back on this design. If the entire premise of myofascial release is physical manipulation, isn't a non-contact placebo kind of missing the mark?
No.
Like, why not just use a light superficial massage as the control group to simulate the physical touch without the deep pressure?
That's a great question, but a light massage would fundamentally compromise the baseline.
Really? Just light touch?
Yeah, because human skin is densely packed with mechanoreceptors. Even a gentle, superficial stroking of the skin triggers autonomic neurovascular reflexes.
Oh, wow.
It signals the nervous system to release neuropeptides that actively dilate local blood vessels and alter fluid dynamics. So if the control group received a light massage, their physiological baseline would be actively shifting.
So they wouldn't actually be a control group anymore.
Exactly. The sham laser is brilliant because it controls for the psychological expectation of healing without triggering a single mechanoreceptor in the lower back.
That distinction makes the measurement data incredibly pure. And to capture that data, the team utilized some really advanced diagnostic technology at baseline, 24 hours and 48 hours post-workout.
The tools they used were top tier.
Yeah, they used shear wave elastography, which is an ultrasound technique that sends acoustic waves deep into the tissue.
Right, and by measuring how fast those sound waves travel, the device generates a structural map. Faster waves indicate stiffer, tighter tissue.
And crucially, it can measure the muscle's stiffness independently of the fascial layer's stiffness.
Exactly. And alongside the structural mapping, they deployed an O2C spectroscope.
What exactly does that do?
So this probe rests on the skin and utilizes a combination of laser Doppler and white light to penetrate up to 8 millimeters into the fascial and muscular layers.
That is deep.
Yeah. It bounces light off red blood cells to calculate local blood flow volume, oxygen saturation, and relative hemoglobin levels.
So we have the submaximal workout, the rigorous placebo control, and the sci-fi measurement tools. And the resulting data just fundamentally rewrites our expectations.
It really flips everything on its head.
Because previous studies analyzing maximal redlining exercise found that severe trauma leaves the muscle relatively unchanged in terms of stiffness, while the fascia becomes incredibly thick, swollen, and structurally rigid.
Right. The connective tissue usually takes the brunt of the catastrophic damage.
But the data from this submaximal trial revealed the exact opposite phenomenon. Across all participants, the stiffness of the extramuscular connective tissue, the fascia remained completely unchanged at both 24 and 48 hours.
The fascia did not stiffen at all.
However, the erector spinae muscle itself demonstrated a significant increase in stiffness across both groups. But wait, if the muscle and the fascia are attached like a wetsuit tightly fitted over the body, how can the muscle underneath get stiff and fatigued while the tightly bound wetsuit stays perfectly normal?
It seems contradictory, right?
Yeah, aren't they mechanically linked?
They are, but if we connect this to the bigger picture, the mechanism behind that paradox becomes clear. It hinges entirely on the edema threshold.
Edema meaning swelling.
Right. When you endure a car crash level of maximal effort, you induce massive micro-tearing throughout the fascial network. The body responds to severe structural trauma by rushing fluid to the area, creating massive swelling. That influx of trapped fluid is what makes the fascia thick and rigid in those DOM studies.
Got it. The wetsuit fills with water and becomes inflexible.
Perfect analogy. But a submaximal effort simply does not cross that inflammatory threshold. You aren't tearing the fascial matrix enough to trigger that massive fluid response.
So the connective tissue maintains its structural integrity.
Exactly. The metabolic fatigue and minor structural strain from those 70% effort eccentric contractions remain localized entirely within the muscle fibers themselves.
Okay, the muscle takes the hit, while the fascia avoids the swelling. And this structural isolation sets the stage for the myofascial release results. Both groups experience muscle stiffness. But the group that received the MFR massage exhibited significantly lower muscle stiffness 24 hours later compared to the fake laser group.
It was a very clear difference.
Yeah, the elastography ultrasound recorded a concrete reduction of 0.66 meters per second in shear wave velocity. The mechanical pressure literally reduced the stiffness of the tissue.
And the researchers validated that observation using a linear regression model.
Oh, the math backs it up.
Completely. By plotting the participants' unchanged fascial stiffness against the binary variable of their treatment group, the statistical model could accurately predict the resulting muscle stiffness.
Wow.
Yeah, this mathematical relationship proves the manual therapy was the isolated variable driving the structural change in the muscle.
Statistics prove the correlation, but we still have to ask how a massage reduces ultrasound wave velocity. Like if the muscle is stiff from cellular damage, how does pushing on the back with an open fist change the tissue structure 24 hours later?
So the leading physiological explanation involves a substance called hyaluronin. It acts as a naturally occurring lubricant between our tissue layers.
Okay, like modal oil.
Kind of. When tissues experience mechanical friction or remain immobilized, this hyaluronin can aggregate and become highly viscous, resembling the thick consistency of honey.
Oh, I see.
And this viscosity restricts movement and increases tissue stiffness.
But myofascial release introduces focused kinetic energy and heat.
Exactly. That kinetic energy disrupts the molecular bonds within the aggregated hyaluronin. Through a process called thixotropy, the mechanical shearing force essentially melts the hyaluronin, returning it to a fluid, oil-like state.
That makes full sense.
Right. Restoring that lubrication allows the muscle fibers and connective layers to glide smoothly again, which then registers as a less stiff environment on the ultrasound.
That is fascinating. So having established the structural changes, the spectroscope data provides a really cool look at the cellular environment. Over the 48 hours following the workout, the overall volume of blood flowing through the lumbar region remained relatively stable across the board.
Right. The sheer volume didn't change.
But the composition of that blood altered drastically. Oxygen saturation spiked by 17 to 21%, while the relative hemoglobin dropped significantly.
And the manual therapy group demonstrated a distinctly sharper decline in relative hemoglobin at 48 hours compared to the placebo group.
But here's where it gets really interesting for me. Hemoglobin is the protein responsible for transporting oxygen to the tissues, right?
It is.
So a drop in hemoglobin sounds detrimental for an athlete trying to recover and rebuild cellular structures. Why would a localized decrease in hemoglobin be interpreted as a sign of accelerated recovery?
Well, we have to evaluate that metric within the specific context of venous microcirculation.
Okay, explain that.
A simultaneous drop in relative hemoglobin alongside an increase in oxygen saturation indicates a highly efficient venous capillary outflow.
Oh, so the blood is exiting the area faster.
Precisely. The vascular network within the fascial layers acts as a drainage system. following eccentric exercise, the tissue is flooded with metabolic byproducts and cellular waste.
Right, the junk from the workout.
Yeah, so the manual therapy isn't necessarily forcing a higher volume of new blood into the region. It's actually optimizing the exit pathways.
Ah, I get it now.
So a lower hemoglobin reading in this specific scenario implies that the deoxygenated metabolite-heavy blood is being flushed out of the tissue much more rapidly in the MFR group.
The targeted pressure basically unclogs the local drainage system.
You nailed it.
And that localized flushing directly influences the final and perhaps most relevant metric for you listening right now, pain. Because this was a submaximal workout, the participants did not experience the agonizing, wincing pain typical of severe DOMs when the researchers palpated their backs.
Right. General pressure pain remained relatively low.
However, the researchers also quantified the pressure pain threshold, or PPT, using a mechanical algometer.
Which is such a cool tool. An algometer is essentially a calibrated plunger.
A plunger.
Yeah. The researcher presses the rubber tip into the participant's lower back, steadily increasing the force. The participant is instructed to say, now, the exact moment the sensation of pressure transitions into a sensation of pain.
That's clever. It removes the subjective complaints and provides an objective measurement of nerve sensitivity.
Exactly.
And at 48 hours post-workout, the placebo group demonstrated heightened sensitivity. Their pain threshold had actually decreased, meaning they felt pain at a lower mechanical pressure.
But the group that received the MFR massage demonstrated a remarkable improvement.
Yeah, they could tolerate significantly more pressure before verbalizing pain. Specifically, an additional 20.69 newtons per millimeter compared to the laser group.
That's a huge difference.
It really is. To put that abstract number into perspective, a newton is roughly the weight of a small apple. Imagine the force of 20 apples concentrated onto a space the size of a pinhead.
Ouch.
Right. That is a substantial amount of focused mechanical pressure pressing into a fatigued back that the athlete is now able to completely ignore.
And this raises an important point, as it perfectly aligns the physiological timeline. The myofascial release utilized targeted mechanical force to reduce structural stiffness in the muscle tissue at 24 hours, likely through the fixotropic fluid changes we discussed.
The honey melting into oil.
Exactly. And by 48 hours, that reduced stiffness facilitated an improved microcirculatory flushing of metabolic waste.
So with less structural rigidity and fewer irritating metabolites lingering in the tissue, the local mechanoreceptors and free nerve endings were significantly less sensitized.
Yes. It creates a cascading domino effect of recovery.
Physical manipulation triggers a fluid response, which triggers a vascular response, which ultimately desensitizes the nervous system.
And the data emphatically validates moderate force manual therapy. I mean, it operates far beyond the realm of psychological comfort.
It's not just in your head.
It's really not. It is a verifiable mechanical intervention capable of altering fluid dynamics, enhancing venous clearance, and objectively increasing an athlete's physical pain tolerance.
So what does this all mean for you? The ultimate takeaway is a fundamental shift in how we view routine exercise. If you are a runner, a weightlifter, or someone simply recovering from a demanding but non-catastrophic training session, your structural reality is totally different from someone who pushed to absolute failure.
Very different.
Submaximal exertion creates stiffness within the muscle fibers themselves, while leaving the fascial wetsuit relatively unscathed.
And if you seek manual therapy to assist your recovery, the clinical evidence absolutely supports seeking out a professional for targeted myofascial release.
Because the moderate depth is what works.
Right. Moderately deep sustained pressure will measurably reduce your muscular stiffness the following day, optimize your tissue clearance 2 days later, and elevate your pain threshold, returning you to your functional baseline with much greater efficiency.
But this research also invites a broader, highly provocative thought regarding athletic programming, right? We have historically treated recovery as this monolithic process.
Yeah, a one-size-fits-all approach.
Exactly. But if submaximal highway mileage workouts selectively target the muscular layer, while maximal redlining efforts catastrophically damage the fascial network, our current approach may be entirely inadequate.
The implications suggest that athletes might require distinctly tailored recovery toolkits based on their specific exertion levels.
That's a paradigm shift.
It really is. A 70% effort on a Tuesday might mandate myofascial release to manage muscular stiffness and fluid dynamics. Conversely, a 100% competition effort on a Saturday might require completely different modalities designed to manage severe fascial swelling and widespread inflammation.
So applying the wrong recovery tool to the tissue could ultimately stall the adaptation process.
Potentially, yes.
Well, the physiological waters of daily training are incredibly complex. For those of you who want to explore the specific mathematics of the linear regression models, examine the ultrasound elastography color maps, or study the exact application angles of the 5 MFR techniques, I strongly encourage you to read the full scientific article.
It's incredibly thorough.
The rigorous placebo control and advanced diagnostic mapping really make it a benchmark in sports science literature. Thank you for joining us today as we explored the hidden mechanics of muscle recovery. Be sure to follow the channel and turn on your notifications so you never miss our deep dives into the science shaping your world. Stay curious, and we will catch you on the